and and those improvements in the future will focus not so much on improving the recoveries of the main metals, but the recoveries of these trace elements. That is my kind of today's feeling, because they are what we are not very much concerned so far. How much then energy is used in copper making? So it is clear or evident, at least based on the previous figure, that these first steps, when we mine the ore, crush it, grind it to fineness which is suitable for flotation, they must consume a lot of energy. And that is also the case. Also the case in copper making. We have examples where this is not true, like aluminium, and perhaps iron. But in case of copper, a lot of energy is used for the first step at the mining site, and that has increasing share in the operations over the last kind of 100 years. This picture is from a recent review on copper production, how much energy in total, how much cumulative energy is used in various steps of copper making. So almost 100 years ago, 1930s, so 30+ percent was of total energy was used in mines. Then the smelting was not efficient at all. It used a lot of fossil fuels for heating and reduction, and very little heat recovery systems were in use. And then this hydrometallurgical part, so electrolytic refining was also rather large in terms of energy usage. 50 years ago, 1970s, we had a situation where still a lot of this pyrometallurgical processing was very old-fashioned. And then already this large-scale mining, open pit mining, and and good quality ores were available, and then the mine site electricity and energy consumption in general was at minimum. And the refining part or electrolytic refining part was improved significantly from that earlier, 40 years earlier situation. So 15 years ago, 2010, and this is trend which is continuing still and will continue. So energy usage at mining site 15 years ago was about how to say 2/3 of total, so 60-70% of total, and smelting, that pyrometallurgy part, that blue part, it was reduced absolutely in absolute terms and in relative terms to perhaps half of what was used in the industry 50 years earlier or 40 years earlier. So there are a couple of drivers, couple of non-industrial and industrial factors which contribute into this trend, and it is easily explained by them. So why this this nice trend of lowering total energy in copper making was possible 100 years ago or 50 years ago, was the reason that there were still good, reasonably good copper ores available, and technology improvements in mining industry were reasonably good and good enough for compensating the lower grades of primary ores. So nowadays, our smelting step is so refined, and it's using so effective processing technologies that it's much smaller than in previous decades, but cannot compensate this mine site usage of energy, which is due to the low very low copper grades, as mentioned there in my previous slide. Let's look at when we had here about 70, 80 gigajoules per ton of copper, the total cumulative use of energy in copper making. So gigajoules equivalent per ton, yes. So we have another metal which is using quite much and much more energy than copper in the smelting step. That is aluminium. And it has a very large impact into the greenhouse gas emissions. Its production volume is slightly larger than that of copper, but still far from the iron and steel industry. So it's if we look at this table, so it's about double the energy usage compared to copper making. And it is mostly because of electricity used in the electrolytic smelting of aluminium oxide into aluminium. So in most cases, not in all cases, but in most cases, that electricity comes from fossil fuel power plants, and then it can easily be compared to the carbon consumption using the efficiency of power plants. But here is also the rightmost columns of this table telling the amount of energy used for processing secondary aluminium into metal, which is practiced in many countries to get aluminium, end-of-life aluminium parts into new aluminium again. So beverage cans and all kinds of aluminium goods, which may have rather short lifespan. So that is only 5% of the primary aluminium making, and it tells why secondary aluminium smelting is interested economically, so as industrial operation also in rather small countries like Finland. So there is no electrolysis needed. The mining part is much smaller in primary aluminum production, so that is not a big deal. But this pure alumina production and so it's digesting and calcination are rather big users of energy, and that means also in many cases carbon. Yes, the ore grades in case of copper, they have been rather dramatically decreasing during this period of those last pictures about copper making and copper industries energy usage. And we see here at early 20th century, so average ore grade or grades, depending how they were made, were about 1.5 1.5 weight percent ore grade, which is 6 times of the lowest levels today, which are used industrially. So the average grade is going down all the way, and here in 1970s it was still 0.6% and 0.4 about 2010. So we see this decrease in copper grade of primary ores as huge increase in energy use in crushing, grinding. And this today, this decreasing primary ore grade has also its consequences in the concentrates and therefore also in the metallurgical operation of the smelters. So what are the side effects of this curve? This curve which is showing rapid downward trend, except some minor eras. Early 1930s and somehow 1980s, late 1980s had a bit higher ore grades as an average. That may be due to discovering some major ores, and they're coming into industrial use. I haven't checked what is the reason for that, but at least in 1930s, copper production was only perhaps 1 million tons, and today we have 23 million tons per year. So a major mining project coming in the stream may have influenced this picture, and it may be the reason why those big kind of peaks show up here. So this is the background for the smelting operations and metal making. We need metals, but raw materials are coming leaner and leaner, and we have also those kind of side effects as our burden. Lower grades in concentrates mean more slag in smelting compared to copper, and more impurities in the concentrates, whatever impurities they are, they need extra effort in the refining step or steps. So in fire refining and in electrolytic refining. And that is why the recoveries in smelting are also declining, not as strongly as in all grades, but really when the amount of slag is increasing compared to the amount of copper in the system. So there is always solubilities and other metal losses, which fundamentally make this total recovery less worse than earlier. Yes, metallurgical industry has always been blamed, and it has a reputation by its soil, water, and air pollution. And this is true, but its elimination has been very kind of slow, because there are very little international rules and actions which would require responsible behavior of the operating companies. And those national rules are often kind of overruled by national interests. So it is a difficult task, and and an issue which should be tackled by the international community, groups of countries, and various alliances better than before. We have in Europe this union of 27, 28 countries forming the European Union, which has been regulating many things in metal making since 70s, 80s. And some 15 years ago, they published the Industrial Emissions Directive, which is giving allowed emission limits for different industries and different elements. And those are based on so-called BREF documents. And those documents are defining the best available technologies, which are called with their abbreviations BATS, best available technique. So those techniques, industrial processes, are the only ones which are allowed to use in EU. So in Europe, at least, we are calling this kind of system license to operate. And each country must take it into account when concerning the total environmental performance of whatever plant it is, not only metallurgical plants. So how they can emit something into air, water, and land, how they generate waste, how they use raw materials, what is the energy efficiency of the operation, what is the noise it spreads into near kind of surroundings, how the accidents are prevented, and how the restoration of the site is managed and taken care upon closure. So it's quite comprehensive legislation, and it goes over the national legislation, whatever national level rules may have had before this into EU members states. This overrules the national legislation. This non-ferrous metals BREF document, the BATS, was updated recently in 2015, and there is, at least concerning the copper making and nickel making in sulfide smelting processes, there are flash smelting technology evaluated as BAT in copper making, and nickel making, nickel matte smelting, as well as in continuous copper matte converting, and their combinations for sure. So this is the legal system in Europe, and my feeling is that geographical areas should follow a similar kind of principle when securing their own kind of state of metallurgical and other operations, and also for being sure that the neighboring countries don't jeopardize the situation in their own country because of some national interest, so to say. Then a couple of words about global emissions of greenhouse gases. We shortly discussed this yesterday, and it is clear that we have selected carbon as the source of heat, as the reductant in many processes of metal making, just because of thermodynamic reasons. It is cheap, it is widely available from several sources, and it is very good reductant. It can separate oxygen from oxides for many different metals, and more effectively than the other possible and affordable reductants. But now this planet has reached the limit. And as mentioned yesterday, the biggest single source of CO2 emissions is iron steel making, accounting about 9% of global CO2 emissions. Luckily, we can produce iron from iron ores using hydrogen or biocarbon instead of fossil carbon. So something which is carbon which has been derived from like farming residues or wood residues. That has been studied a lot recently in Aalto. And hydrogen, if it is based on non-fossil energy like wind energy, solar energy, hydroelectric energy, well, nuclear as well. So then we can produce steel without coke and without coal as fuel and as reductant, without any greenhouse gas emissions from the steel plant. And this conversion, technological conversion, is just now under development in many countries and in many big iron and steel companies. You may know that iron and steel making has very big companies which are capable of producing process development by themselves. But then again, if the driver is not hard enough, so it happens like here, that a small Nordic steel company, together with electricity provider and iron ore mining company, have decided to build fossil-free iron making. And that kind of semi-commercial plant has been operating in Sweden some years now, and there is decision to build a commercial demo plant in northern Sweden, in Luleå, which should operate 2027 to make this sponge or DRI, direct reduced iron, for melting in arc furnaces by electricity. So this hydrogen here is made either in hydroelectric plants or wind, solar power. So without any fossil ingredients, so to say. And the reduction equipment is a shaft furnace, which is, to my understanding, it's almost commercial technology, which can be utilized in pellet form of ores, or like in this hybrid scheme, or as fluidized bed reduction. As you know, there is no carbon-free steel available, because there doesn't exist such metal as steel without carbon. So all steels are classified based on their carbon content. So that is why at some stage here, carbon must be added into this DRI. so that steel can be produced in melting and secondary steel making for casting and rolling. So this is basically rather similar route for iron ores to steel than the present one. There are lookalike operations, pelletizing, blast furnace, converting. So converting means removal of carbon to CO2, and then the same secondary steel making step, which is identical to this hybrid. But what is big, so to say, question mark still is the operation in the solid state, low temperature, reduction of fine iron ore by hydrogen. That takes place at 700 perhaps, and it is something which must operate on the same scale as blast furnace, which is quite a challenge. We know that biggest blast furnaces today are operating at the annual production rate of perhaps 10 million tons. Not 1,000 tons, but 10 million tons. So they are still, there are still a lot of engineering problems to solve, and this hydrogen making and storage is also problematic. Nobody has done it on this scale before, and the electricity needed for that is huge. So we need a lot of windmills. We need a lot of PV fields for extracting solar energy from the radiation and wind, and that must be continuous operation from one year to another. So there are a lot of engineering challenges in front of us, and this is not regarding the scale of steel making and total production of the steel making industry. This is not a small challenge at all. Okay, let's go back into these best available technologies. So they are freely available documents, reference documents, which are covering all industrial activities once practicable, and you can browse them in the web. So they provide descriptions of of a range of industrial processes, not going into details, in the smallest details. But for example, their respective operating conditions and emission rates. And these are, as I said earlier, these are the rules every member state in EU must follow and take into account when some industrial operation is kind of started. So it is a very strict legislation, and lot of time and effort was used for writing and accepting these briefs. They were not written by kind of by the countries or by the authorities, but mostly by industrial people. So they are not, their background is not in the kind of rules as such, but it is based on the technologies and knowledges we have about the processes and their possibilities at the moment of kind of compiling those documents. So they are not results of typical legislation making where politicians and authorities were kind of saying or dictating what must be done. But there are the kind of evaluation of industrial opinions. What is the state of art today, and how it should be generalized and used in the future. Okay, then let's go a bit deeper in the copper production of today, and as a kind of introduction here, I took one sketch of Dowa mining from the previous millennium, 1998, which is quite correctly, to my mind, in classifying the various steps in copper smelting and refining. One exception is here the level of converting. In 1998, continuous converting was not commonly used, and if somebody would redraw this schematic, there would be two converting options. So conventional bath converting and continuous converting, but that does not change the big picture very much at all. So here we have the pre-treatment level of operation. So some technologies need roasting, drying, or sintering in the for the feed of the smelting step, and this is and was perhaps very much so in 1998 when still electric furnace smelting was used and reverb smelting and blast furnace smelting. They are relatively rare today. So in that sense, we have in practice only 2 pre-treatments for different technologies, no pre-treatment or drying. So then smelting step includes electric furnace, reverb, flash smelting furnace, blast furnace, and continuous Mitsubishi furnace, which are producing copper matte. And those facilities, electric furnace, reverb, blast furnace, depending on raw material basis, they were close to this matte grade range, lower range, 30 weight% copper, whereas flash furnace and Mitsubishi could do it in somewhat better way and produce 60-65 weight% copper. In addition to these matte smelting technologies, there are a couple of Chinese new methods which have gained some use in, say, within the last 15 years, and also this originally Cyrosmelt name technology, which is commercialized nowadays with 2 names, one being Isosmelt and the other being Osmelt technologies. So these are bath type of smelters, but they all nowadays produce matte. All right. So this is the big picture of copper making technologies, and we have many steps here which are vulnerable for SO2 and carbon dioxide, CO2 emissions. And this is one reason why some technologies are fading away, so they don't provide the environmental performance which is needed today, and they are gradually closed or replaced by more modern variations of copper making. So copper smelting has also carbon dioxide emissions because the smelting step may need extra heating for raw materials, for off gases, to keep them at that temperature where the process continuous operation is possible. And there is a general trend of reducing these CO2 emissions, and also this has been one of the reasons why some technologies are not competitive or have not been competitive anymore. So this is statistics from originally from Brook Hunt 2009 edition, showing the carbon dioxide emissions of other processes, other technologies than flash melting, and that is about 1.4 tons per ton of copper. And here is the performance of flash melting plants. This is not predicted performance. This is actual plant data reported to Brook Hunt some 15 years ago. So if we compare this value, which is less than 1 ton CO2 per ton of copper, so this includes all, for example, usage of oil and gas in foundries where anodes are cast, and oil usage in flash melting furnace, or coke usage in converting. So this is total CO2 emission reported by the company. And this is less than one ton per CO2 per ton of copper. And just keep in mind that iron making in blast furnaces consumes today about 1,465 tons of CO2 per ton of product, so hot metal, big iron. And if we compare, this is no excuse, but just compare the impact on the global atmosphere. So the global production of hot metal last year was almost 1900 megatons, so million tons. But copper mine production, which is that part of copper which goes through smelters, it was only 22 megatons, million tons. So this is the ratio is about 95. So steel industries, in terms of CO2 emissions, it's 95 times the emissions of CO2 in copper industry. So that is why this is not the main issue in copper making. This was a main issue in copper making in 60s and 70s, namely SO2 emissions, because most copper smelters in the world, they exhausted all SO2 in the atmosphere. And that caused acid rain in many industrialized regions, like in Europe, and that acid rain killed forests in Central Europe a lot, and that was a main environmental concern. It also kind of washed away old buildings, because acid rain is acid, and buildings, stone buildings from the past, they typically are built out of sandstone or limestone, which both easily react with slightly acidic rain and they crumble down. Today, the problem has been solved practically. There are still countries which are exhausting most sulfide smelter SO2 in the atmosphere. Russia is the worst example. And why and how this was this was solved is quite easy to understand with my next graphics. So this figure 20 shows this is kind of sales argument to flash melting, but it shows the real reported or calculated SO2 emissions from about this blue line from about 1970s. And this red line shows the behavior of SO2 emissions if those smelters which were converted to flash melting technology would have continued to operate. And this is something which is rather dramatic. It took 20 years from 1970s to 1990s before SO2 emissions really started to go down, and this green area is the estimated reduction of SO2 amount from those smelters which converted their processes, and the SO2 emissions from flash melting is here. So it's very small compared to total emissions, and once technologies for and legislation for capturing SO2 from off gases was compulsory, we could see that it is going down quite rapidly from 1990s onwards. This is not the only. Well, this means that 96 million tons of H2, SO3, so sulfuric acid, was not formed in the upper atmosphere, and it's really big impact into the greenhouse effect and acid rain in particular. So this graph shows the last bit of that development from early 1990s until 2010. So it is clear that some 30 years ago there was a huge difference between sulfur capture capability of flash melting technology compared to the other technologies. Flash melting was capable of capturing more than 90% of SO2, and these are again plant data, not kind of nameplate data, not kind of literature data. These are data from the emissions estimated by the companies, and sulfur capture data from the companies. So the huge gap between the other technologies which were capable of fixing less than 50% of all SO2. And this means that pressure from societies have forced companies to change their technologies into such which is capable of doing the job, fixing the SO2 and saving the environment from acid rain. So we know that to be profitable, a smelter must take care of constant process improvements, like metal value recoveries in their production. This is something which cannot be over kind of emphasized. In EU area of Europe, there are 8 major primary copper smelting companies, which are producing about 2 million metric tons of copper each year. And that is based mostly on primary raw materials, on sulfidic concentrates, but to increasing extent also on scrap. And they may, 2 of them may be actually the biggest copper recyclers, and e-scrap, so electronic scrap recyclers in Europe. And this graph shows how the 8 smelting companies have performed in terms of total energy consumption. So the trend has been first declining clearly. About 1/3 has been disappeared from their total energy consumption. That's megajoules per ton of copper. So gigajoules are certainly 5, 10, 15, 20 gigajoules per ton of copper. And this could be explained by the excessive use of copper scrap in the companies. And that particularly means e-scrap, so electronic scrap. Why it has not been decreasing, maybe reason of several factors. One being certainly the more complicated concentrates and raw materials in general, and requests to recover more and more, so increase the resource efficiency. And it really has happened. So this is the trend of scrap usage. So this is new scrap. This is something which is coming internally from copper semis fabrication plants, which are producing quite much of this so-called no, sorry. This is really the old scrap usage in companies. So not including this internal circulation of copper scrap, which is typical to copper industry. When they produce semis, there is a lot of residues which are remelted, and that is seen in copper production as on top of the mine production, and it's typically 10-15% of total, and And this is showing the old scrap, the end-of-life goods scrap usage, and its increase over that period of time from early 1990s to early 2000, how it has been increased, and it is perhaps one of the reasons for lower total energy usage. And this increase here, which is certainly this tons or kilotons per copper per hour, has increased, it doubled during this period of time, from 8 to 17%. And it is still half of the total usage of recycled copper because of this primary scrap, new scrap usage, which is so-called traditional use of copper in the smelters. So what is important actually in recycling, and this is the challenge of our societies in the future, and has been some time already, is how we get all this metal, old metal, from end-of-life goods to back from the kind of dumps and waste materials. How we can organize our societies in such way that the metal really requires for recycling of the companies. So we call that old scrap collection rate. How much of the material or metal which was sold a couple of years ago, perhaps 10 years ago, or half a year ago when you bought a new cell phone, how much of that material is collected for recycling? And then the question is how well we can separate different metals from those collected old scrap amounts we have available. And that is not 100%, it is far from that on the average. And then we have also a definition, end-of-life recycling rate, which is defining based on metal what is our capability of recycling that specific metal. So we compare, in copper recycling, we compare pure copper from electric wires and its recycling rate, and then how much copper we can get out of brass, or when brass is containing, in addition to copper, it contains zinc. We may also ask how much out of that zinc we have, what is our capability to recycle that zinc? Is it 10%? Is it 20%? Is it 50%? And this UNEP document from 2011 has evaluated by metal these old scrap, post-consumer scrap recoveries. And they are amazingly low. If you look at this blue color, so we see blue color in quite many areas of this map of periodic table. Chromium, yes, I wouldn't expect anything else, because stainless steel is the end use of chromium mostly, and it is collected. It looks precious. It looks valuable. Doesn't roast. It doesn't corrode. It's easily to find amongst the other steel type of scrap. Iron, yes, it's available in vast quantities, has been used and recycled long time. It's over 50. Nickel as well, because it's mostly going along with chromium in stainless steel. And then we have some lead, amazingly cadmium and mercury. That may be due to some international limitations of using cadmium and mercury in batteries and so on. But otherwise, I'm surprised that these are blue. And then this group of metals: rhodium, palladium, iridium, platinum, silver, and gold. Certainly, they are recycled well after use, because everyone knows that they are valuable. But then there is lot of metals in the range of 1 to 10% recovery recycling rates. This is tantalum, antimony. Yeah, that's ruthenium, and even smaller, less than 1%, osmium, gallium, germanium, arsenic, indium, thallium, bismuth, lithium. So there's a large variety and of recoveries and recycling rates, and this is something which is in our focus point as nations and as professional metallurgists. So that recovery rate does not tell very much about how much that metal is actually used in metal production as input to the production processes. And this is also something which is kind of confused by the increase of demand of metals all the time. So in areas like copper, aluminium, iron, where the growth rate in demand has been quite high over the last perhaps 100 years. So it cannot be, and they are parts of investment goods, bridges, national grids, locomotives, all kinds of things which are not cheap and not discarded easily. So this is something which is horrifying people who don't know and understand the structure of metal industry and metal demand in particular. And it's something you must understand the background and explain things based on the structure of the usage of each metal. Some are used in very short end of life times, and like lead typically, and some like copper are aging very slowly. They have long lifetime. Then there is an issue of critical metals, which seems to be expanding every year. So many countries have defined or geographical areas have defined critical metals or elements, which they say that there is a poor availability, and they claim that these metals are critical, and those lists are based on the estimates how the future will be, and also how kind of what the mineral resources on each geographical area have. Not very much on the headlines or on the agenda of political decision makers is the critical metals belonging to those minority trace metals of typically sulfide ores, but they are all oxide ores, which are can be included. And those metals are often called high-tech metals, which are used in various displays or electronic components: antimony, indium, gallium, selenium, tellurium. They are examples of those metals, high-tech metals. They are separated and produced based on their demand and sales price on the market, and they remain in the side streams of the smelting and refining if the price is not good, if the price is not covering the resources used in the metal making. And in many cases today, these metals are on the tailings areas of those smelters. And it has been analyzed by one US research group that copper smelters and zinc smelters have residues which contain quite much of the demand, future demand of these metals. And to me, it shows that this question of these technology metals being critical because they are not produced by the smelters is not the demand, which is non-existent, but the price, which is very low. So the demand and price go together. If there is demand, price is higher, and when there's no demand, price is lower. But it is true that these metals are not produced, but that is question of economic situation. There is also an UNEP report from 2011, including some estimates of recoveries or yields of precious metals in processing, which are rather curious to me. So that report claims that processing old scrap of rhodium, palladium, platinum has a end-of-life recovery rate only close to 50%. And for gold and silver, even on a level of 15, 20, or 30, 50%. This is something which is truly unbelievable to me, because many smelters in the world believe that their PGM recoveries and gold and PM, precious metals recoveries, are essentially 100%, and they can't determine whether that is 98 or 102%. So be careful when you are reading reports from even though those rather high respectful organizations like UNEP. All right. This is end of my sustainability session of this course. And I will continue next week with copper and nickel smelting. But Imam, I think we have time for
Yes.
one or two questions.
Yes. Okay. Okay. Okay, guys. Questions, please. You can raise your hand, and then I will pick from the raise hand one. Please don't be shy. And tomorrow you will see me. Tomorrow will be very boring. It's very academic thing, face diagram. So yesterday and today lecture of VK is kind of introduction. The real course will start tomorrow. Lecture about copper will start next week with PK. We still introduction. Okay. Please, if you have any question, please don't shy. Anyone? You know, it's very interesting because they say if one student asks, then another will ask. Okay, everyone understand? Yesterday we have a lot of questions. It seems they are shy, Becca. 100 student, more than 100 student. Everyone, no questions? Okay, guys, if there's no questions, then thank you, Becca. So see you next week. And tomorrow you will see me, everyone. And thank you very much. Thank you,
Thank
Becca.
you.
Bye bye.
Bye-bye.
Bye bye.